Hello and good morning. Welcome to this presentation on creating 5G test scenarios, the constraint random way. My name is Keshav Kannan and my colleague Eric Kim. We both work at Intel Corporation. Let's proceed. This is the agenda for today. We will go over system level test scenarios and I'll briefly touch upon the 5G specification and how we broke it down, followed by a conclusion. All right. Constraint random verification at system level is considered extremely difficult due to the size of the solution space, the number of parameters that comes, and their interdependencies. Traditionally, constraint random has been limited to the stimulus generation, and rarely it is applied at test scenario generation when it comes to a system level verification. So here, our attempt is to shift constraint random to test the scenario generation at the system level. Let us see what we're talking about when we say system level test scenarios. All right, let's talk about traditional versus constraint random system level test scenarios. Now, traditionally, system level test scenarios have been limited to directed and feature centric, which rarely is used to measure coverage and is also very difficult to create many test scenarios. Whereas constraint random test scenarios, we have the test scenarios are generated constraint random way, and we are able to generate all of the feature-centric scenarios, and moreover, we can also easily create corner case scenarios and performance and throughput scenarios. Now, if you see the graph here, we see that the directed methodology is a linear curve, whereas in the constraint random, you see there is an initial development phase, but after that, you see that there is a definite gain both in terms of quality and productivity. Of course, the downside is that the complexity is significant with respect to the constraints, but we'll look at how to deal with it in the future slides. To talk about the impact on results, we did verify a 5G NR communication system with over 400 high-level CR test scenarios. In addition, we also added coverage measurement for the scenarios itself to see how good the quality of the test scenarios were. And at the end, we did catch about 80, actually a little over 80 critical RTL bugs, which would have otherwise caused a hang. And yeah, on top of this, it was very easy to create performance tests, stress tests, and throughput scenario tests to verify the design's robustness. And one of the advantages we had was that the constraint random infrastructure could be completely reused at top level and all the unit levels. And another advantage was that we could replay a failing test at one level, take it to another level. For example, a test fails at top level, we could rerun the same exact scenario at a unit level to see what exactly was the difference in the functionality by comparing the waveforms or seeing what was different in the functionality. All right. To talk about the magnitude of the problem, a typical 5G communication system has 64 instances of user equipment. Well, 5G is also is measured in the granularity of one slot, where you can have 64 instances of UEs, inserting 3-channel types into each slot: PUCCH, PUSCH, and SRS, which are basically control data and sounding in 5G terminology. Now, if you see this chart, we have 64 UEs, the number of UEs marked on the x-axis, and number of parameters you have to deal with on a logarithmic scale on the y-axis. If you see for 64 users for 3 channel types, we have over 11,000 parameters to deal with. Now, if you have to deal with 11,000 plus parameters in a typical use case, the randomization load on the tool is going to be significant. Plus, the code, the constraints that you have to write is also going to be pretty massive. On top of all of this, if there is a constraint failure during your simulation, the debug analysis of the constraint failure is also very challenging. Okay, let me briefly introduce you all to the 5G specification. So 5G specification, the 5-layer communication channels in the uplink and downlink typically has, like any other protocol, communications protocol, has synchronization reference signals. In this case, we call it a primary synchronization signal, PSS, SSS, PBCH. There are signal strength indicators and tracking signals, PTRS. And we have control signals such as PUCCH, PDCCH, and data channels like the PUSCH and PDSCH. Multiple users are mapped to specific resource elements in the frequency time domain uh, in the shared resource grid. So, top resource grid is formed based on system level parameters, RRC parameters, and user level parameters. Number of antennas, radio frequency, subcarrier spacing, maximum bandwidth. These are some of the parameters that decide the shape and size of the resource grid. Now here in this diagram, we see one slot, which is basically if you see 14 symbols on the time domain, and number of RBs represented in the frequency domain, and basically each, if you see here, the total bandwidth allocated here is 66 PRBs. PRBs are basically physical resource blocks. Whereas the actual bandwidth part that is we are allowed to allocate in this particular example uh, is between the second RB and the 18th RB on the frequency domain. Now, there are, if you see these blocks within the bandwidth part, there is UE1, UE2, UE3, and the brown boxes are basically the data, PUSCH. The dark blue box here, for UE3, is control, PUCCH, and the dark brown UE1 here is SRS, again spread over 4 different symbols in the resource grid. So this is an example of how channel types for various users are allocated in a resource grid. All right, let's talk about 5G frame structure. We'll talk about frames, slots, symbols, subframes, etc. Numerology or mu, which is basically subcarrier spacing configuration in the 5G NR. We have different numerology values supported. And if you take a frame, which is divided into 10 subframes, overall 10 milliseconds, and each subframe is represented by one slot in the case of um, numerology equals 0, and each subframe, like I said, is one slot, and each slot is further divided into 14 symbols. Now, based on the numerology selected, you will have the number of slots per subframe or the number of slots per frame vary. All right. In the frequency domain, we see resource blocks, and each resource block represents 12 consecutive subcarriers, and a subset of contiguous common resource blocks is called a bandwidth part, which is where all our allocations in the frequency domain are limited to. It is always a subset of the entire bandwidth that is available for our allocations. This slide talks about channel types with respect to what kind of constraints they apply on the constraint random engine. for during its allocation. So each user equipment can have different channel types that can who sit on a resource grid. They share multiple users, like I said, can share the same resource grid with different channel types for the same user. Now each channel type has specific parameters, and these specific parameters define the placement of the resource on the resource grid. Constraints involve like no, you cannot have two channel types overlapping each other in the resource area. And yeah, all your constraint random generation must ensure all of the 5G NR specification is not violated, or any of the specification requirement is not violated while allocating these channel types. All right, let's break it down further. So to break down the problem of constraint random generation, we applied a simple divide and rule uh, idea on this. So we identified logical stages where the randomization can be broken down. At a very high level, we broke it down to three stages for the 5G test scenario generation. The first stage being system level configuration, G node B parameters, which is the antenna parameters, bandwidth, numerology, impairments, and interference. Now, these are really high level parameters which decide how your resource grid will look like. And on the stage two, we broke it down into the user equipment related parameters. Each user equipment, if we need 10 users to be randomized in a particular scenario, then we have so many UE parameters to deal with, and all the RRC parameters that are relevant to that. And until now, we have dealt with all the parameters for all the slots that are going to be static. And stage three is where we actually randomize the channel types for every user for every slot, which means these are dynamic parameters for every user for every slot. Going into details of how to break it down, in stage one, we randomize the RE grid, where some of the parameters that we deal with at this stage, which will never be touched upon again in the next stages of randomization, would be the bandwidth, the FFT size, the subcarrier spacing, and the bandwidth per CC or carrier frequency, timing and frequency offsets. And all these information is used to build the resource grid based on the number of. So every time you run a test, you say, okay, I want number of slots to be tested now is 10 slots, and I want to test 4 CCs. And you mentioned these, and then the resource grid is built for the desired number of slots and CCs. Stage two, we will go and randomize all of the UE configurations, the bandwidth path size, the resource block group size. There are a lot of other parameters that we randomize that is UE specific. All of the PU, CCH, PU, SCH, SRH specific parameters for the UE at the UE level are also randomized here. We also decide which channel type will keep repeating in which slot and what intervals. And yeah, all these parameters of the user config classes objects are for number of users for each CC. So moving on to the final stage of the breaking it down process. This is the final stage where we actually go and insert the channel types into the resource grid. So at this point, we have the resource grid ready and all the UE configurations are ready for the number of users that we intend to randomize into the resource grid. So the user sequence here defines how the insertion is to perform or to be done, and what channel types need to be inserted. And so we break it down further. The stage three is a series of randomizations depending on the sequence needs. It will insert one channel type for one UE at a time into the slot, and it inserts as many channel types as you want. And yeah, so it refers to a common resource map where it sees for an empty unallocated area and make sure all the specifications constraints are met while inserting the channel type into the slot map, into the resource grid. So we look at the common resource grid. In this case, this is the common resource grid that is uh, a static grid, which is an enumerated grid. And if you see here, we are setting up the grid in such a way that it can be have a maximum number of CCs that we intend to simulate, and the number of slots, and the number of symbols, which is in 5GNR is fixed to 14 symbols, and the number of RBs, that is the max resource blocks that is possible in the 5GNR scenario, which is typically 273, 275 RBs. And like I mentioned, this resource map, RE grid map, is going to represent your entire time domain and the frequency domain allocation. And this is what will be uh, randomized at the end of your randomization cycle. So a typical user sequence, well, there's no hard and fast rule how the user sequence needs to be, but here is an example where we are inserting PUCCH and PUSEH and SRS inserted into for every UE, into every, in this case, we are looping through every UE, every CC, and every slot. And we can change this the way we want. We do not want PUSEH. We want to test only this and this. We don't need this. So every time we hit randomize, a PUCCH for a particular UE is inserted into a CC and into a particular slot. And yeah, this is an example, and it can be done any other way, the way user wants. So here's a list of features that were covered from the uplink perspective. It's just an idea to get an idea, give an idea as to what could be achieved with the constraint random scenario generation. Pretty much covered all the tough scenarios in PUSCH, PUCCH, and SRS with respect to an uplink perspective. And here is an interesting analysis, randomization load analysis. Randomization load analysis for a 64 UE insertion of one type of PUCCH and one type of PUSCH and SRS into one slot. If you see number of parameters defined for just to insert the first stage of randomization is about 30 parameters, and the second stage, all the UE configs is about 69 per user, and each PUCCH format 0 would take about 30 parameters and about 50 parameters for PUSCH and about 24 for every SRS for every user. All of this is per user. Now, if you take the number of randomization calls it would take for the first stage would be one randomization call, and you randomize 29 parameters and you're done with the first stage. The second stage, the stage 2, you will randomize all the UE configs, and it takes about under 5,000 parameters. And the remaining channel types are inserted one by one, like I mentioned, for all the 64 users. The total parameter count that we dealt with in this randomization was over 11,000. Now, if you had not broken down the entire problem, we would have to deal with 11,000 parameters at one randomization call, which is an extremely complex problem, whereas we have broken it down into 257 randomization calls in this case. All right, to conclude, constraint random system level test scenario generation has been made possible. Some of things we did cover that constraints have to be divided hierarchically. This means that you can easily maintain constraints the way when you break it down. We saw that we broke it down into 3 high-level stages. Now this also means that your constraints also are getting divided and it is more manageable. And secondly, the randomization calls itself went through a divide and rule. So we didn't have one randomization call. Instead, we had multiple randomization calls. And this also helps with your debug and implementation. And thirdly, we have the common resource grid in the 5G realm. And this made it possible because all the randomization calls refer to the same resource grid. And finally, the user still has the complete control on how the test scenario is generated using the sequence. And with all this, yeah, we did achieve constraint random system level test scenario generation applied at a 5G NR system. Thank you. All right, I have some time. I'm open to some questions at this point. Thank you.